In this video, we're going to look at L'Hopital's rule. We're going to recognize when we can apply L'Hopital's rule. We're going to identify the indeterminate forms produced by quotients, products, subtraction, and powers, and then apply L'Hopital's rule in each case, and then we're going to describe relative growth rates of functions. So the first thing we want to do is determine whether or not we can use L'Hopital's. So one of the rules is that it must be 0 over 0. So in other words, when I do an evaluation as x approaches a, or as x approaches infinity or negative infinity, then my function in the numerator will go to 0, and my function in the denominator will also go to the 0. If that's true, then we can use L'Hopital's. As x goes to a, or as x goes to positive or negative infinity, we take the limit as x goes to a of the numerator or the denominator, and if that's true, and we end up with infinity over infinity, or negative infinity over negative infinity, then we can apply L'Hopital's. What is L'Hopital's? L'Hopital's rule says, if we have the case where it's 0 over 0, or infinity over infinity, then all we have to do then is take the derivative of the numerator separately than the derivative of the denominator, and then we can reevaluate. If we still end up with 0 over 0, or infinity over infinity, or negative infinity over negative infinity, then we can use L'Hopital's again until either we can do a direct substitution or we can no longer apply L'Hopital's. So we're going to use L'Hopital's to evaluate these limits. Now, for a here, I would not use L'Hopital's. I would use what we learned in our previous videos, which is I would divide each one of these terms in the numerator and denominator by the highest power in the denominator. But let's show you that L'Hopital's does work, and it will work multiple times. If I were to insert infinity into here and into here, I would have the infinity over infinity case. So L'Hopital's does apply. So what I'd like you to do when you are using L'Hopital's is to state that you are by using L-hop. So you're telling me you're using L'Hopital's, and that's how you got to the next step. So we have the limit as x goes to infinity. Now if I do the derivative of the numerator, I'm going to get 12x squared minus 4x, and then the derivative of the denominator. Note this is not the quotient rule. I'm doing the derivative of the numerator separately than the derivative of the denominator. And when I do that, I'm going to get 3 pi x squared. Once again, if I try to do a direct substitution, I'm going to get infinity over infinity. So that tells me I can use L'Hopital's again. So again, what I'm going to do is I'm going to do equals. I'm going to note that I'm using L-hop. And that is a terrible L with an apostrophe. That is like the worst of the worst, L-hop. There we go, L-hop. And I have the limit as x approaches infinity. My numerator, when I do the derivative of the numerator, I'm going to get 24x minus 4. And then in the denominator, I'm going to get 6 pi x. Once again, if I were to do a direct substitution, I would get infinity over infinity, so L'Hopital's still applies. So I'll do it again. Noting that I did L'Hopital's, so I do the limit as x goes to infinity. I'm going to get 24 over 6 pi. Now there's nothing left for me to actually evaluate, so I end up with 24 over 6, which is just 4 over pi, and that is my final answer. Now, like I said, I would not have done that by L'Hopital's. What I would have done is I would have said, oh, let's divide everything by x to the third. Every term by x to the third, and so I end up with the limit as x goes to infinity. I don't know what happened there. The limit as x goes to infinity of 4 minus 2 over x plus 6 over x to the third. And then I'm going to have pi plus 4 over x to the third. As x goes to infinity, this goes to 0, this goes to 0, this goes to 0, and I end up with just 4 over pi. Just because you can use L'Hopital's doesn't mean you want to use L'Hopital's. I'm just saying that you're allowed to, as long as we end up with infinity or 0 over 0. Let's take a look at b here. So we have the limit as x goes to 0. If I were to put 0 in here, I would have the sine squared of 0, which is 0. I would have 0 in the denominator. So this is of the form 0 divided by 0. So L'Hopital's does work. And I'm allowed to use it. So by L'Hopital's, so I'm going to note it as L hop. I'm going to take the limit as x goes to 0. I'm going to do the derivative of the numerator first. It's going to be the chain rule, so it's going to be 2 the sine of 3x, now the derivative of sine, which is the cosine of 3x, and then the derivative of 3x, which is 3. In the denominator, I'm going to get 2x. Once again, if I try to do a direct substitution, I'm going to end up with 0 over 0. So L'Hopital's is still a valid thing that we can do here. So we have the limit as x goes to 0. Now it's the product rule in the numerator, so it's going to be 6. I'm going to do the derivative of sine first, so I'm going to get the cosine of 3x multiplied by the cosine of 3x multiplied by 3. And then plus, so when I put in the derivative of the second one, so I'm going to have 6. The derivative of cosine is negative sine of 3x multiplied by the sine of 3x multiplied by 3. My derivative of the denominator is just 2. And now I can do a direct substitution. Wherever I see the sign, when I do a direct substitution, it will go to 0, so that will all go to 0. Wherever I see cosine of 0, it's going to go to 1, so these are going to go to 1. So I'm going to be left with just 6 multiplied by 3 divided by 2, so I end up with 18 divided by 2, which is 9. And that is my final answer. So for this, I have the limit as x approaches pi over 2. Well, pi over 2 is going to go to infinity. The tangent of pi over 2 as x approaches pi over 2 from the, and I should note that I'm coming from the left, is going to be infinity. From the right, it would be negative infinity because that's the shape of the graph. Now, secant is the reciprocal of cosine, and as cosine approaches pi over 2, we're going to approach 0. That means this is also going to infinity. So I end up with infinity over infinity. So now I'm ready to do the derivative. By L'Hopital's, I can do this. So L hop. And I can't do an L with an apostrophe today to save my life. There we go. So we have the limit as x approaches pi over 2. The derivative of tangent is secant, so 2 the secant of x. The derivative of the denominator, well, that's secant squared of x. It's secant tangent, but I have the chain rule, so I have 2 the secant of x multiplied by the derivative, multiplied by the derivative of secant, which is secant tangent of x. So that's what I end up with. Well, I have secant squared over secant squared, so these two will cancel and give me just 2. So I'm going to end up with the limit as x approaches pi over 2 of 2 over 2 the tangent of x. Well, I guess those 2's also cancel, so let's go ahead and cancel those back here. And so I'm just going to get 1 over the tangent of x. Now the tangent, as we talked about, the tangent as x approaches pi over 2, and I do need to note I'm going from the left. So as the limit as x approaches pi over 2 from the left, that's going to go to infinity. So I basically have 1 over infinity. I'm not using L'Hopital's. It's just the fact that the tangent as x approaches pi over 2 from the left will become very, very large. And so this is going to be equivalent to 0. Let's take a look at my example D here. Now, the fact that it's y does not mean anything. We're still going to look to see whether or not I'm going to get 0 over 0 or infinity over infinity. If I were to put 2 in here, I would get 4 plus 2 minus 6, so this is 0. If I put 2 in here, I'm going to get 8 minus 4, the square root of that, so that's square root of 4, which is 2 minus 2, which is 0. So this L'Hopital's does apply. That's the first thing I always want to do. I am disinclined probably to do L'Hopital's because I see the square root there and I'm thinking this is going to be nasty for derivatives, but we're going to do it with L'Hopital's. I probably wouldn't do L'Hopital's. So let's go ahead and do L'Hopital's, and so we have the limit as y approaches 2. The derivative of the numerator is just going to be 2y plus y, and then the derivative of the denominator, well, remember I'm doing the square root of 8 minus y squared. That's derivative is going to be 1/2. 8 minus y squared raised to the negative 1/2 multiplied by a negative 2y. Just that portion of it. So I'm going to have 1 over 2 multiplied by, I'm going to write this as 1 over, do it this way. I'm going to write this as negative 2y over 2, the square root of 8 minus y squared minus 1. And the reason I'm going to do that is I'm going to do some algebraic cleanup and hope that things cancel out. Let's see what happens. So I'm going to go ahead and multiply. Notice here that the 2's cancel. I'm going to multiply everything by the square root of y minus 1. And when I mean everything, I mean the numerator and denominator, each term. The square root of 8 minus y, the quantity squared. And the reason I'm doing that is because of this fraction. It's a complex fraction of a fraction within a fraction. So I'm going to get the limit as y approaches 2 of 2y plus y. And then I'm going to have the square root of 8 minus y squared. In the denominator, I'm going to get negative y minus the square root of 8 minus y squared. And if I were to put 2 in at this point, let's see what happens. If I put 2 in here, I'm going to get 4 plus 2, so that's okay. I'm going to get the square root of 8 minus 4, so that's the square root of 4. These are going to be multiplied together, so that's not 0, so that's okay. I put in 2 here minus, and it'll be a negative 2 minus the square root of 8 minus 4, so it's the square root of 4. Oh, so I can do a direct substitution at this point. So when I do a direct substitution, I'm going to get 6 multiplied by 2, because that's the square root of 4. I'm going to get negative 2 minus 2, because that is the square root of 4. So I'm going to get 12 over negative 4. So my answer is negative 3. Provided I didn't make any algebraic mistakes. Okay. Now, there are other forms in which we can use L'Hopital's. If I have 0 multiplied by infinity, 0 multiplied by infinity, or infinity minus infinity, what I can do then is I can do some algebraic manipulation to make it become a form that allows us to do L'Hopital. So I need to take the 0 multiplied by infinity and force it into a 0 over 0, or I need to force it into an infinity over infinity. The way I'm going to do that is by algebraic manipulation. So let's take a look at our first one. Example A here. As x approaches 1 from the left, I'm going to get approximately here is going to be 1 minus 1, which is about 0. And then this is going to go to infinity. So this is 0 times infinity. Now, I know, this is going to be a side note, and then I'm going to erase this. If I have a over b multiplied by b over c, actually I'll do d over c, indecision, and d over c, then this is going to be a over b multiplied by c over d. Notice how division of fractions means that we multiply by the numerator fraction by the reciprocal of the denominator fraction, and you're thinking, what does that have to do with what I'm doing here? Well, if I have a multiplied by b, I can write this as a divided by 1 over b, because this is b over 1. Because if I would have had a divided by 1 over b, I would take my numerator fraction, which is just a, and multiply by the reciprocal of the denominator fraction, which is b over 1. I'm going to use this a lot here to make it be either 0 over 0 or infinity over infinity. So I've got to decide which one is going to be the easiest for me to do the derivative of, because then I can use L'Hopital's, right? So I think it's going to be easier to do the derivative of 1 over 1 minus x than it would be 1 over the tangent. So I'm going to rewrite this as the limit as x goes to 1 from the left of the tangent of pi x over 2 divided by 1 over 1 minus x. Now I've got to see whether or not doing it this way is going to allow me to do L'Hopital's. When I put in 1 from the left, this is going to go to infinity. If I put in 1 from the left here, this is going to be 1 over 0. And what does that mean? Well, let's just take a look at the graph of f of x is equal to 1 over 1 minus x. Now, this is the parent function of this is the reciprocal function. It has a reflection and a shift. So let's rewrite this as negative 1 over x minus 1. Why did I do that? Well, because then I can clearly see this is the reciprocal function. Reciprocal function, the parent function looks like this. And I am going to shift it over to the right one. So this is going to shift this asymptote right one. So it's at x is equal to 1. And with a negative here on the 1 in the numerator, all this does is reflect this graph. And so instead of increasing from left to right to x equals 1, I'm going to be decreasing. So I'm going to be decreasing, and instead of increasing from left to right as x moves away from 1, then it's going to be also decreasing. So this confirms that if I have it in this form, I'm going to go to, in fact, I'm going to go to actually negative infinity, which is okay. It's okay to have positive infinity over negative infinity. So let me go ahead and erase this. Just was confirming that I can set it up this way. Now let's go ahead and do the derivative. By L'Hopital's, we're allowed to do this. So this is equal to, by L hop, it's going to be the limit as x approaches 1 from the left. I'm going to take the derivative of a tangent, which is secant squared of pi x2 multiplied by pi over 2. And then in the denominator, I'm going to get, well, the derivative of the denominator, since this is 1 minus x raised to the negative 1, its derivative is going to be negative 1 minus x raised to the negative 2, and then it's going to be multiplied by a negative 1. So this will become 1 over 1 minus x, the quantity squared. So then the question is, did we solve what we needed to for L'Hopital's? Well, let's go ahead and try to plug in 1 from the left. So when I try to plug in 1 from the left, I'm going to get pi. I'm going to have over 2, the secant, because there's a reciprocal of cosine. This is going to go to infinity. Oh, and this is going to go into infinity. And I didn't get what I wanted. I ended up with infinity over infinity. So I didn't get what I needed. So probably trying to do the easy way out of 1 over 1 minus x probably didn't help me. So let's go back and write it as the limit as x approaches 1 from the left of 1 minus x over 1 over the tangent of pi x divided by 2. Now let's see if this helps at all. So we know that we can write this as the tangent of pi x divided by 2 raised to the negative 1. So then its derivative would be negative 1, the tangent of pi x divided by 2 raised to the negative 2 multiplied by the secant squared of pi x, pi x, pi x. So pi x divided by 2 and then multiplied by that derivative of that angle, which is pi over 2. All right. The derivative of the numerator, though, this is really kind of nice. So by L hop, I'm going to get the limit as x approaches 1 from the left. The derivative of the numerator is just negative 1. In my denominator, I'm going to have a negative 1 multiplied by pi over 2. So negative pi, all right, this is negative pi over 2. The tangent squared raised to the negative 2 of pi x divided by 2 multiplied by the secant squared of pi x divided by 2. So then this is just, let me do some cleanup here. This is going to be the limit as x approaches 1 from the left of 2 divided by pi. Tangent will go back into the numerator, so tangent squared of pi x divided by 2. Secant squared of pi x divided by 2. And I end up with infinity over infinity. But let's write tangent as the sine squared of pi over 2 over the cosine squared of pi over 2. And then it's going to be multiplied by the secant. And so it is, so it's then divided by the secant, which is 1 over the cosine squared of pi 2, pi x divided by 2. These are all pi x's. Let me go back and change those. Pi x's divided by 2. Pi x divided by 2. Pi x divided by 2. Pi x divided by 2. So we know that it's going to be the numerator fraction multiplied by the reciprocal of the denominator fraction. So I'm just going to get sine squared of pi x divided by 2. Oh, well, that's lovely. So not using L'Hopital's or anything, this is just going to be the limit as x approaches 1 from the left of 2 divided by pi, of the sine squared of pi x divided by 2. And as x goes to 1 from the left, this is just going to give me the sine of pi over 2, which is just 1, so my answer is 2 divided by pi. So even though I had a start where I wanted to not do the chain rule on tangent, I had to end up doing the chain rule on tangent, but it wasn't really that bad. It wasn't like great, but you know, of all the things that we've done, it wasn't that bad. Let's take a look at our next example over here. So we have the limit as x goes to infinity of x minus the square root of x. And this is kind of the form of infinity minus infinity. All right, so if I have infinity minus infinity, let's see if I can factor out an x. We should be getting used to this one. We have the square root of x squared plus 1. I can factor out an x by writing this as the square root of x squared 1 plus 1 over x squared. And so this will give me the absolute value of x, the square root of 1 plus 1 over x squared. Since we're going to positive infinity, we don't have to worry about the absolute value. And so we can rewrite this as the limit as x goes to infinity of x minus x, the square root of 1 plus 1 over x squared. Now I'm going to factor out an x. I'm going to get the limit as x goes to infinity of x, and then I'm going to have 1 minus the square root of 1 plus 1 over x squared. Now as x goes to infinity, this is going to go to, well, this will go to 0. And so I'll have 1 minus 1, which is 0. So I have 0 times this infinity. So we know what we're going to want to do then is rewrite this as the limit as x approaches infinity, and hopefully get the one that is the least amount of work in the denominator. Unlike last time where I did a start and stop and didn't work out well. So I have 1 minus the square root of 1 minus 1 over plus 1 over x squared divided by 1 over x. Now I have infinity, or I have 0. What do I have? I have 0 over 0, because as x goes to infinity, this will go to 0. So I have 0 over 0, so I can use L'Hopital's. So L hop. So I have the limit as x goes to infinity. Well, in the numerator, the derivative of 1 is 1, so then I just have to worry about this part, which is the square root of 1 plus, I'm going to write this x raised to the negative 2. Its derivative is going to be 1/2, 1 plus x raised to the negative 2 raised to the negative 1/2 multiplied by negative 2x raised to the negative 3. So my denominator is going to be 1/2, and I'm going to clean it up as I go. This 2 and that 2 will cancel, so I'll get negative 1 over, I'm going to write this as x cubed, over the square root of 1 plus x raised to the negative 2. And then in the denominator, right, the denominator, this is just going to be negative 1 over x squared. So let's clean this up and see what happens. See if we are done, or if we have to do L'Hopital's again, or if we went down the wrong path, which I hope not. These negatives will cancel, and I'm going to have 1 over x cubed multiplied by 1 plus x raised to the negative 2. I'm going to multiply by my reciprocal of my denominator fraction, which is x squared. And so I have some nice cancellations. This just gives me x. So I'm going to have the limit as x goes to infinity of 1 over x multiplied by 1 plus 1 over x squared. Now I can do direct substitution. As x goes to infinity, this will go to 0. This will go to infinity. So I have basically infinity on the denominator, which we know goes to 0. A lot of algebra in this section. All right, let's take a look at the last two. Well, D is going to be similar to what I just did, so I'm probably not going to do D, but let's take a look at C. If I put in 0, this is going to be 0, but this is not going to be 0. So it's going to be, well, infinity, right? Because x can't be 0 for this square root part. And so that's going to go to infinity. So I have 0 times infinity. I'm going to try to decide which one is the easiest. Well, remember that 1 over the square root of 1 minus x over x is the same thing as the square root of x over 1 minus x. So it may be better to do the derivative in that form. So I could rewrite this as the limit as x goes to 0 from the right-hand side of the sine of x divided by the square root of x over 1 minus x. And then I can do the derivative, and I'll let you all go from there. And D is similar to B, so I'm disinclined to do that one. Because I really want to get into this form. Well, what happens when I have 1 raised to the infinity, 0 raised to the 0, and 0 raised to the infinity? These are also indeterminate forms, and what we're going to do is we're going to use the fact that we can take the natural log. So if we go back to our log rules, and remember when we had the square root rule for the limit, well, we can do the same thing with log rules. We have this rule that says, hey, if I have y is equal to f of x raised to the g of x function, then I'm able to take the natural log of both sides. I have the natural log of y, and we know this other side will become g of x multiplied by the natural log of f of x. So then if I take the limit of both sides, the limit as x approaches a, the limit as x approaches a. Then I'm going to have the limit as x approaches a of the natural log of y is equal to the limit as x approaches a of g of x multiplied by the natural log of f of x. Now, that's all good and well. So what else do we do? If the limit as x approaches a of the natural log of y is equal to L, then the natural log of the limit as x approaches a of y also equals L. All right, cool story. Now what? Well, remember by my exponential rules, if I take e raised to the natural log of something, it will equal that something. So the limit as x approaches a of y is equal to e to the L. You're like, okay, but we didn't start out with y. No, what we started out with was this. So the limit as x approaches a of f of x raised to the g of x will be equal to e raised to the L. So now let's really apply this. So that's the reason we're allowed to do it. I wanted to give you the reason why and not just say, just do this. I always find it's better to give reasons why. So the first thing we're going to want to do is replace it with y equals 1 plus 4x raised to the 3 over x. Take the natural log of y is equal to, I'm going to have 3 over x, the natural log of 1 plus 4x. Now I'm going to take and do the limit. So the limit as x approaches 0 of 3 over x, the natural log of 1 plus 4x. This is the same thing as the limit as x approaches 0 of the natural log of 1 plus 4 over x over x. I'm going to bring that 3 out front. If I try to do a direct substitution, I would have the natural log of 1, which is 0, over 0. So let's go ahead and use L'Hopital's. Now we're going to use L'Hopital's, so by L hop. I'm going to get 3 multiplied by the limit as x approaches 0. The numerator derivative is 1 over 1 plus 4x multiplied by 4. My denominator is just 1. Now I can do a direct substitution. As x goes to 0, this becomes 0. So I'm just going to end up with 3 multiplied by 4 all over 1, so it's 12. But that's not my answer, remember? Because I started out with this. And I showed you that we now have to take and undo this natural log shenanigation. And so if I undo this natural log shenanigation, it's going to be e raised to the 12, because way back here, I had the limit as x approaches 0 of the natural log of y, which is equal to this, until I have to undo that, so my answer is e to the 12th. So don't forget that it is not just 12, it is e to the 12th, because of all the steps we had to take to get there. Let's take a look at this next example. So if I try to put in 0, I'm going to have 0 raised to the 0. So I'm going to do y is equal to the sine of x raised to the tangent of x. This is going to give me the natural log of y is equal to the tangent of x multiplied by the natural log of the sine of x. Okay, so if I try to put in 0, this is going to go to 0, so this is going to go into infinity. This is going to go to 0, so I have 0 times infinity, which is an indeterminate form. Prior to that we just did, so I'm going to rewrite this as the natural log of the sine of x divided by 1 over the tangent of x, but that's the cotangent, so I have the natural log of the sine of x over the cotangent of x. Now, if I were to try to do the limit now, I'd make sure that I can use L'Hopital's. I would have 0, the cotangent, or this is going to go to 0. Sine is going to go to 0, which means natural log is going to go to negative infinity. Cotangent, as we go to 0, that's going to go to positive infinity, so that is going to work. So now I'm ready to do the limit as x approaches 0 from the right is going to be the natural log of the sine of x divided by the cotangent of x. I am allowed to use L'Hopital, so I will. So L hop, the limit as x approaches 0 from the right-hand side, I'm going to have 1 over the sine of x multiplied by the cosine of x. My denominator, the cotangent, is negative secant squared. Negative cosecant squared. Negative cosecant, CSC squared of x. So this is going to be equal to the limit as x approaches 0 from the right. I'm going to have cosine x over sine x. Cotangent is the same thing. This cotangent is 1 over the cosine squared of x. So then I'm going to multiply by the reciprocal, which is going to give me the sine. This is going to be 1 over the sine squared of x. So this is going to be the sine of squared of x. So this sine and one of these sines, and so I end up with the limit as x approaches 0 from the right-hand side of the cosine of x, the sine of x. I'm going to put in 0, and I don't have to do anything more, and I'm going to get 0. Because the sine of x will be 0, the cosine of x will be 1, so I get 0. That's not my answer. My answer is going to be e raised to that number L, so e to the 0, which is 1. So my final answer for that is 1. Because remember, all of this stuff is just allowing me to get to the point of finding that number L, and then I need to go back and say my answer is e raised to that L number. Okay, let's take a look at this example. As it stands now, if I put in infinity, this is going to go to 1. This is going to go to infinity, so this is 1 raised to the infinity. So y is equal to 1 plus 1 over x raised to the natural log of x. The natural log of y is equal to the natural log of x multiplied by the natural log of 1 plus 1 over x. If I were to try to do this infinity, this would go to infinity, this would go to 0. So I need to rewrite this some more. So the natural log of y is going to be the natural log of 1 plus 1 over x multiplied by 1 over the natural log of x. Now I would have 0 divided by 0. So I'm now ready to do the limit. The limit as x approaches infinity of the natural log of 1 plus 1 over x over 1 over the natural log of x. L'Hopital's does apply, so I can use it, and I'm going to use it. I'll hop. And the limit equals x goes to infinity. In the numerator, I'm going to have 1 over 1 plus 1 over x. And then the derivative of 1 over x is going to be negative 1 over x squared. My denominator, since this is the natural log of x raised to the negative 1, its derivative is going to be negative 1, the natural log of x raised to the negative 2 multiplied by 1 over x. So this is going to be negative 1 over x multiplied by the natural log of x, the quantity squared. This negative and that negative will cancel out. Let's do some algebraic cleanup. I have the limit as x goes to infinity. I have 1. Well, let me deal with this. So I'm going to deal with that up here. 1 over 1 plus 1 over x. Let me multiply every term by x. So I can get rid of the complex fraction. I'm going to have x over x plus 1. So this is going to be x over x plus 1 multiplied by 1 over x squared. And then we're going to multiply by the reciprocal of this denominator fraction, because this is the numerator fraction multiplied by this denominator fraction. The reciprocal of the denominator fraction will be x, the natural log of x, the quantity squared. This x, and this x cancels, so I end up with the limit as x goes to infinity of the natural log of x, the quantity squared, over x plus 1. Now, up until now, we were done. We can do a direct substitution. We're done. We cannot do the direct substitution yet, simply because if I were to put in x goes to infinity, this will go to infinity, and so will this. So I will have to use the L'Hopital's again. So by L-hop, again, L-hop, I'm going to get the limit as x goes to infinity of 2 the natural log of x multiplied by 1 over x, all divided by 1. So this is going to be the limit as x goes to infinity of 2 the natural log of x divided by x. And then we'd ask ourselves, can we do the direct substitution? And the answer is still no. All right, so we're going to do L-hop again. This is kind of a long one. L-hop again. It's going to be the limit as x goes to infinity of 2 multiplied by 1 over x multiplied over 1. Now we can do direct substitution, and this is just going to be 0. Still not my answer. This is L. And remember, I need to write it e to the L, which is 0, so my answer is 1. So there is my final answer for that one. That was a long one. There was a lot going on with that. That was a long one. A lot of algebra, a lot of remembering, my rules of logs and exponentials. A lot was going on. Okay. I'm going to let D be yours, because I know this is a long video already, and I don't want this to be like super long. So I'll let D be yours. You're just going to do your natural log of both sides, and then take the limit, and then all of that. Okay, growth rate functions. Suppose a function f and g are both approaching infinity as x approaches infinity. Although the values that we have are fairly large, what will happen is that typically one function will grow faster than the other function. So we want to know which one is growing faster. So if the limit as x approaches infinity of g of x over f of x goes to infinity, or the limit as x goes to infinity of f of x over g of x goes to 0, then we know that on this case, the g of x is going to be dominated, and on this case, the g of x will be dominated. It's going to grow rapidly, because we know if this is growing faster, this is going to make dividing by a large number go to 0, whereas this one, if g of x is the larger one, then f of x will never be able to catch up, and eventually it will dominate and it will be infinity. Okay, so on the other hand, if we do the limit as x approaches infinity of f of x over g of x, and it becomes a number, then we say that they're growing approximately at the same rate. So we need to determine which one is growing faster. So what we'll do when I have x raised to the 100 over 2 to the x is I'm going to do the limit as x goes to infinity of x raised to the 100 over 2 to the x. So I ask myself, can I use L'Hopital's? Well, yeah, this is going to go to infinity, and yeah, this is going to go to infinity, so let's use L'Hopital's. When I do L'Hopital's, I'm going to get the limit as x goes to infinity of 100 x to the 99, and then I'm going to have 2x, the natural log of x, natural log of 2. And this is going to go on for a long, long time, right? This is going to go on for a long, long time. So how am I going to figure this out? Well, eventually, what I'm going to do with a whole bunch of L'Hopital rules, is I'm going to end up with, I'm going to do a bunch of L'Hopital's. Let's assume I've just done a bunch of L'Hopital's. I'm going to end up with the x goes to infinity, and I'm going to have 10 factorial. Why am I going to have 10 factorial? Well, the next one is going to be, the next derivative is going to be 100 times 99, and the next one will be 100 multiplied by 99 multiplied by 88. So I'm going to have 100 factorial. Cool. In the denominator, I'm going to have 2 to the x, and then I'm going to have the natural log of 2, and that's going to be raised to a large number. If I had to do the derivative of this, I had to do this derivative 100 times, that means I must have had this raised to the 100 times. And then the question is, well, which one is going to dominate? Well, this 2 to the x is still going to be much larger as x goes to infinity over 100 factorial. And I'm not saying 100 factorial isn't large. 2 to the x will eventually dominate, and so this will go to 0, which means 2 to the x is the one that actually dominates over, and it's going to grow faster. Let's take a look at the next one here. So I'm going to have the limit as x goes to infinity. I'm going to have 10 to the x over x to the 10. Now, the limit by L'Hopital's, because if I were to try to put in infinity, I'd get infinity over infinity. So I'm going to have the limit as x approaches infinity of 10 to the x, the natural log of 10 over 10x to the 9th. This is by L'Hopital's. L-hop happened. Well, we know again that we're going to do L-hop a bunch of times. The limit as x approaches infinity of, well, I'm going to have 10 to the x, the natural log of 10, because it's just a constant. I'm going to do this 10 times, and I'm going to have 10 factorial in the denominator. Again, 10 to the x is going to dominate, and so we know that 10 to the x is going to grow much faster. This will grow much faster, which is typically true. Exponentials grow way faster than polynomials, and this confirms it. And that's it for this video. Not as long as some of the other ones, but still not a short one.